Okay. What did I do? I'm recording.
We've got to set it up so that you can stream directly to YouTube. That'd be great.
Yeah, just stream directly to YouTube. Everything I say in my office gets streamed directly to YouTube. That would be horrible. Okay. All right. So the project is due Thursday, February 4th. Do not wait until the day before to get started. At the very least, this week, you should go in, make sure you can connect to Mentor Graphics through the remote desktop. There's directions in the project folder that you can open your team folder because some people, ITS doesn't quite get your permissions right. Generally, if you're a TA, sometimes there's weird reasons, but whatever. Just make sure you can open your folder and create a project. There's directions specifically for creating a project in the project folder in BB Learn, because I realize you haven't done that before, and it's new anyways, because everything's changed. And so I went and updated all that. Most of the things in the project, it just looks like it's one sentence, but the one sentence will be create a schematic and create a cell underneath your new library that you've already created in BB Learn, in Pixis, that and then create the schematic and put it in there. Those one lines can take you an hour a piece. So be careful with that. And I've also got a rubric posted which tells you how many points each one of those parts is worth. And I literally go through and I just check for those things. If I see anything that I feel like you need to fix before project 2, I will let you know. Generally by taking a point or 2 off for that. You can get some of those points back on project 2, or they will count for fixing those. If you don't fix them, you won't be able to do project 2. So at least open up the files because it can be
You'll be in your office tomorrow.
I will be in my office tomorrow. I was in my office today too. Wait, what's tomorrow? Wednesday? Yeah, I was in my office hours last week on Wednesday. I was just doing them at home. I had an attitude moment. I sat on my couch. I did my office hours at home. I was reading a book. I had the whatchamacallit, the video off, so nobody could see what I was really doing, and mostly just answering questions about EE490. Okay, because they had a homework due that day. Second day of class, of course. So we are getting into, we talked about this a good bit, different ways of packaging to reduce delays. Delays really matter, and a lot of the delays now aren't just reading the memory out of the chip, but getting it across the board to the processor. Please, when you're making your own Linux file names, do not put slashes in your file name. It makes your file a directory underneath itself, and we can't open it. And I don't know how to fix that. And even Clint doesn't know how to fix that. Do not put spaces in your Linux file name. Again, it thinks it's a different file and you will never be able to open it again. No dashes, no stars. Use letters and numbers. Use your suggested file names. Generally, numbers are okay, but I wouldn't start a file name with a number because there's some programs that don't like that. It's just a bad practice. Okay. Where we were. We're on the 3rd generation. Synchronous DRAMs. The idea is to get through all of this today. Okay. So in the 3rd generation, we added this amazing new feature called a clock. All hail the clock. It made things so everything happens at the same time. You can increase the speed because you don't have to wait for things to settle. You just wait a clock cycle. Everything's doing their settling at the same time. We don't have to wait for the individual pieces to settle. All commands, all operations. Wait, why is this not working? Sorry. I'm going to have a minute here.
Technical difficulties.
Technical difficulties. I need the pen.
You need to have like elevator music queued up for when technical difficulties happen.
Draw with touch. Somehow that looks promising. No, I can draw with my touch, but I can't draw with my pen. Oh, now my pen works. Okay, I take all that back. Your technical difficulties are now solved. Let's go back to my pen. All commands are executed on the rising edge or the falling edge of the clock. We'll just assume it's rising edge, so I don't have to keep saying that over and over again. This is not the DDR generation. DDR came later, the first DDR. And DDR, you see that on a lot of memory chips. They'll call it DDR5 or DDR6 or whatever DDR numbers in production. When we were at Micron, they were doing like testing and stuff for DDR6. I don't even know.
The publicly, I think 4 is still the like cutting edge, more or less.
Okay, so they're going beyond that already, trying to get beyond that, but yeah. What they're doing, they're always speeding things up. So DDR is, and why is this not working again? I can't touch it with this. I've got to hit the thing that says, okay, whatever, it's working now. DDR, it means double data rate. And basically speeding up the timing within the chip causes a lot of problems. They have to speed up the timing of everything. With DDR, they're only speeding up the timing of the output. They're triggering on both edges of the clock. They are not truly triggering on both edges of the clock. I had this discussion with Daniel Eichenberger. And I smacked him around a bit at first. Basically, what they are doing is they are triggering a time delay off the rising edge. And that gives you, they're basically dividing the clock into 2 periods. But it's effectively about the time the falling edge would happen. Clocks are never 50% duty cycle, and the duty cycle varies with time. So what you would do is, if you're actually triggering off the falling clock edge, is, let's say it's 100 nanosecond period on the clock. Sometimes you trigger here for your first clock edge at time t equals 0, and sometimes you trigger at 47 nanoseconds, and sometimes you trigger at 53 nanoseconds, and there's no telling with clock jitter how far apart that would be, and it would vary with time, and it would drive the people trying to read this out crazy. So don't do that. They actually do like a fixed 50 nanosecond delay using a phase lock, time lock loop after that clock edge.
Oh, is that the thing from the reading where it's like at a signal frequency of like 150 or 120 femtofarads or something like that? Or no? What?
No.
There was something like that in the reading last night.
No, it wasn't in last night's reading. That would have been way ahead. And that might even be like in my one of my analog classes. We're going to take the input and output data, and we're going to multiplex that. Because remember, before we had a data in and a data out pin. Now we don't want to have to write and read 1 bit at a time. We want to be able to read a byte at a time or a word at a time. So we're going to need, like, to read a word at a time, we're going to need 16 pins. So 16 input pins and 16 output pins. We might as well put them together and make them our data pins. So DQ is both for our data in. Oh, great. This is going to drive me crazy. It's just dying on me. Data in and data out. I have to push a button, not with my pen, but with my finger when this thing hangs up. Okay. It's like doing how to do several things at the same time again. So that's what we're going for. So here is the pinout. Basically, the signals we have on the pinout, we have BDD and BSS. We have a second supply, VDDQ and VSSQ. We have 16 data pins. And this is because my 64 megabyte is now 4 megabytes of address space. And I read out a word 16 bits at the same time. So they're going to come out in parallel on these 16 data lines. They'll also be written into the device in parallel on those 16 data lines. Now I have to, 64 meg is an awfully big chip to actually write. So another thing I'm going to do is I want to divide this up into banks. So I've got 64 megabits, that's a little b. And I'm going to divide it up into 4 banks, which actually represent 4 different die. And each one of these is 16 megabits. And my battery is dying. So we have another technology moment while I go and plug in the cord, which is right down here because I keep rolling my chair over. Right there. Okay, so we got power now. And each one of these is called a bank. So for each one of those banks, bank 0, etc., I'm going to need 2 bits to address which bank I'm talking to. Okay. Beyond that, 64 meg is 2, 4, 8, 16, 32, 64 is 26 address bits. Is 26, 2 to the 26, 26 address bits. Okay. 4 of those I can get rid of because I'm really only addressing 4 megabits. Wait, more than that. 4. Where did I get 4 from? 5. 4 megabits would be 22. Yeah, 4. But I really only have 4 mega addresses because I'm addressing 16 bits at a time. So that's going to give me 4 meg is 22 address lines. So I don't need that many address lines. 22. 2 of them are used for the bank. Oh, I've done 22. 12. I don't understand that. 4 megabytes, 22. And I have 12. I'll just skip over that for right now. So if somebody calls me on that, I'll try to explain it. Or not. And I have 12 address lines coming in. These are multiplexing addresses between the rows and the columns. I think that's a typo. Is my best explanation at the moment. There's a lot of typos in the Keith book. We've got RAS and CAS. Those are the address strobes for the row and the column. I've got a clock and I've got a clock enable. I've got a chip select to turn the whole chip on so I can power it down or put it into sleep mode when I'm not using it, conserve power. And I've got a bit that enables my write. And I've got some other signals that are used for the I/O mask. So when I'm actually looking at this thing, this is what the chip looked like. One thing to know, all the signals I talked about before, VDD, let's go down through here. This is important to understand. VDD, VDD, those are all the VDDs I see. Here's the 3 VSSs. We're putting multiple connect lines in for the power supplies, and that's to lower the impedance. The resistance, the inductance, and the capacitance you see looking into that pin of that package, is significant enough that when you go through a single pin, VDD on this side does not look exactly like VDD on that side. If they put multiple pins in parallel, it reduces the resistance, it reduces the inductance. You get a better signal over on this side. Okay, so that's why they use the extra VDD pins. Let's look at the data rate. So I've got a clock that can vary between 100 and 143 megahertz. It's a 64 megabyte chip, and I get 16 bits out at a time. And 16 bits is 2 bytes. So I'm transferring 16 bits on each clock cycle. We want to figure out what the data rate is, and this is in megabytes per second. F clock tells you how fast it can give you 16, I'm getting one signal, one packet of data out at 100 megahertz. Now I'm getting 2 bytes out at 100 megahertz. I'm now getting 200 megabytes, capital B, per second, just by having those multiple output pins on there. All the things you need to understand for either homework 1 or homework 2. And if I'm pushing my clock speed up to 143 megahertz, then I would get 286 megabytes per second. And there will be no confusion with the between this S and the complex frequency in here, because I won't talk about complex frequency in here. Just say yay, no Bodie plots. Now DDR stands for double data rate. All of the logical commands going to the chip tapping on the rising edge of the clock, but I'm getting data out, I'm buffering the data, and so I can write the data out on both the rising and the falling edge of the clock. I get twice the data rate, which means I can get now 400 to 572 megabytes per second. Now, there's logical conclusions to this, and we'll talk about this in more detail later. I can't even tell you all the stuff Micron's doing. They're a year and a half ahead of me now, and some of the stuff I was sworn to secrecy when they told me. DDR2, which is an old standard now, it's also called quad data rate, and basically it means that, okay, so here comes my clock. My old standard is I get data out here and I get data out here. When I go to DDR, I'm going to get data out here, I'm going to get data out here, I'm going to get data out here, and I'm going to get data out around the next falling edge. When I go to DDR2, I'm going to get data out here, data out when there's not even a clock edge, data out here, data out here, data out here. I'm getting 4 times the data rate out.
Is it sort of an exponential thing? So like since DDR2 is quad data and DDR1 is like double data, yeah. Would DDR3 then be like 8 times the data? Mm-hmm. And then 4 would be 16 and et cetera. Okay. Now there's this wonderful thing you've never heard about, unless you're Corey Klein, and he got this from me in one of his classes independently. Okay, it's called It's called a phase lock loop. Did you get anything about that in 348? No, not in 348, but I got it when Corey told me about it. Oh, okay, good. And now it is
about having technology. Okay. Oh, great. I can use my finger. I cannot use my stylus. Let me see if my battery's going dead. That might be a simple explanation. I have these wonderful things here. They're called Quad A batteries. Okay, so what a phase lock loop does is it looks at a signal and it calls the leading edge of the clock 0 degrees. And it wants to put, and it's going to want it for DDR2, it's going to want to put a pulse out at 90 degrees. So it measures that edge, looks for something that's a 90 degree phase shift away from that, and will put a signal in then. So it's actually measuring either the phase delay, or you can think of it as a time delay, a quarter of a cycle time delay later. It's going to produce a pulse that will actually act as a clock for the data output, and it will be locked in with what the system clock is. Yes, and now things are working. Batteries.
Does speeding up the clock itself instead of that just cause issues then?
Yeah, okay. Normally my first choice would be to just speed up the clock.
Okay.
But the problem is if you just speed up the clock, all the logic inside the memory chip, there's a little microcontroller on there, also has to speed up. And if the microcontroller speeds up, it's going to dump a whole bunch more heat into the system. And DRAM doesn't like heat. So
Okay.
it's better just to have a smaller section on the I/O operating at a faster speed and having the main chip operating at the lower speed.
Okay.
That was the explanation I got from Daniel Eichenberger.
From the DDR2 shift, so there's 4 subsections within every clock in that sense. And you're saying it was based off of the, like, it's a phase shift in it?
Yeah.
Okay.
It's a phase shift, but it's for a digital clock, it's easier to think about this as being a time shift. So what it's going to do, if this is, that didn't help. I can use my fingers now. Okay, if that was 100 nanoseconds, for some reason, oh, okay, this is 100 nanoseconds. Then what you want to do is 25 nanoseconds after that edge. You kind of measure where this edge is, and then you wait 25 nanoseconds and you throw another clock pulse. And then 50 nanoseconds, you throw another one. And that will give you much more reliable timing than we'll be looking at those clock edges. Because what happens in a real clock is this edge here between the clocks, the 100 nanoseconds part is pretty stable. But where this edge falls on the falling edge tends to jitter around a lot. It varies with time. And if you're relying on that, you're not going to have very reliable data timing on the output. It's better to just add the extra analog circuit in.
I feel like with if DDR2 is already that fast and they're already experimenting with like DDR6 and 7 at Micron,
yeah.
Is there a point where the clock is almost irrelevant because data is just going out so fast?
Okay, I will tell you what I saw. Okay, so they're in this one system they're looking at. They are, the data's coming out. I forget the numbers, so I'm just going to make it. Let's say the data's coming out at 10 gigahertz. And the guy who's doing this is the really high up analog guy at Micron, and he only has a 10 gigahertz scope. So the clock at this point, the clock that they're generating for the data, looks like a sine wave because the higher order components aren't even going through. The next thing they're doing, and I'm not going to tell you how they did this because it's magic and it's kind of funny, is they don't wait for the data output to settle before they decide if it's a 0 or 1. They look at the slope of the data, and they look at the past 3 bits, and determining based upon what the state of the past 3 bits are and the slope of the whether it's rising or falling or staying the same, they're going to decide whether it's a 0 or 1.
Absolute witchcraft.
It is. There's all kinds of analog stuff going on even within a memory chip. Not everybody working at Micron deals with this stuff, but they have a small analog group that yeah, that just to deal with things that other people would think were in a memory. So the block diagrams gotten a little bit more complicated, but most of this, oh, behave. Okay, most of this is just depth. It's like when you build your 8-bit microprocessor in EE490. Building a 64-bit microprocessor is a lot of repetition of the parts of the 8-bit microprocessor. So I've got 64 meg. There's 4 banks. These are actually 4 individual die in there. They still have their sense amps on there. I still have my address lines coming in. They go into a register that stores them, decides if it's a row address or a column address, and will either enable this multiplexer if it's a row address or this multiplexer if it's a column address. Go out and they need to decode the bank addresses and the row addresses and decide which areas in here they're actually turning the rows on. You've got a column decoder in here. Now inside of the banks, if I'm writing to it, I would take the data in from my data bits, wherever they are. There they are. The data comes in to the input register, gets stored there, and gets routed to the correct place depending upon what the data is and what column you're addressing. The output comes from a specific group of 16 columns also, and that goes into the data output register. Probably a buffer, some kind of FIFO or something like that, if you know what that is, where they can get stored. A FIFO is a first in, first out memory. It's exactly what it sounds like. When I spit the data into it, that will be the first data I spit into it will be the first data to come out, and it just keeps on advancing things up like that. At least that's what I would do. Okay, now writing. In order to write enable has to be true, so it's low, it's got a star next to it, and CS has to be true. This is a warning for your Mentor graphics names. Do not call your signal WE star, whatever you do. Remember what I said about numbers and slashes and things like that? Linux doesn't like it. And ultimately, Mentor as a GUI will take those things in. But when it processes it through Linux, Linux doesn't know what to do with things like this. So what we would do is we call this not write enable.
We need to just have a whole list of things you're not allowed to name files in Mentor.
Write enable bar. Use letters and numbers. Okay. So the write enable's low. The chip select is low. So those are both true. Next thing I want to do is I want to open a row. And to open a row, I put the row address in, and then I pull RAS low. In RAS. Once the column is addressed, once the row is addressed, I can address the column. RAS always comes before CAS. The column address, I pull column address strobe low. I put the column, I change the column address change to the column address, pull column address strobe low, and then the data will be written to that memory location. So that is the most basic version I can give you of how this timing works. Now, I told you inside of these things, there's a little microcontroller. You remember back from your EE490 days where you had like these various control registers for your microprocessor. And you had command registers for your microprocessor. This is how these things are working. If I want to do a no-op, there's several ways to do a no-op, but I can set my external signals looking like this, and I just basically set my external signals. We haven't quite gotten that far yet. I'm setting my external signals up like this. If I want to select the bank and activate a row, I'm going to have to set up my signals like this. And you can build your timing diagrams based upon you doing your operations. This is the external timing. We haven't gotten to the control registers yet. I got ahead of myself. This is not stuff you should memorize. This is stuff you look up for the particular memory device you have. If you understand the basic operations, that's more important. The RAS before CAS and some basic timing than memorizing these dates. Not this again. 15. Oh, I did change slides. It just looked amazingly the same. So all these different things we can do. We can, and in addition to the basic reading and writing and putting it into burst mode, pre-charge is usually done, the timing is done by the internal controller. You can set up the auto refresh, put it into refresh cycle. There's other little commands you can do here. They change from week to week. Okay. Now here's another thing that I want to be able to do. My output clock is slower than I can read the data out, because once I address the row, all the column data is available immediately. If I want to read out that whole row, 16 bits at a time in packets of 16 bits, I'm probably getting the data out faster, and I want to be able to buffer the data as it's coming off the array before it goes to the output, because the output's clocking slower than the data's coming out. So I'm changing the column address here. I'm in state A, and then I want to be able to read state B because I can do that faster, and then state C, and some amount of time, and 3 cycles later, state A comes out on the output. So there's a lag in here to make up for the fact that I'm reading the data out faster. You could also have a latency of 2, which would get you out like 1 clock cycle faster, but being able to store the data internally will speed up how fast you can output it. Because the thing that takes the longest is addressing the row, always addressing the row. And then you can store data, and then probably second after addressing the row, the next slowest thing would be writing the data to the outside world. And then the third slowest thing, the fastest thing would be actually accessing different packets of data within that row. So there's tricks you're going to play to be able to get that working right. Mode register. Just like in 215 with microprocessors, I told you I got ahead of myself. We have these registers here that set up the actual chip mode of operation. Again, not something you memorize, something you look up for the device you're dealing with. The burst length is set by these 3 bits, and I don't know what that means. BT, the burst type, is it sequential or interleaved? The CAS latency, I can set that. Most of these reserved things, if you set them into the reserve state, it does weird things to the chip. Don't do that. Just go, what I would always do back when I was doing this, as I go through, this register bit by bit, figure out what mode I wanted it in, write down the binary equivalent of that register, convert it into hex, and then that would be what I would write. And I would not think about it again. I give that mode a name that made sense to me, and I'd put that in the comments. Sounding like a programmer more and more every day. This is what happens when you take 310. The question I nearly really wanted to ask Becky today, but I knew I shouldn't. Does anybody want to hear this?
I do.
Okay, so he had this thing where he's writing down module. This is how I think, and this is why programmers hate me. And then there was some other nonsense, and of course there's a semicolon at the end. What I wanted to know, my deep first burning question is, do you put the brackets in? Now you understand why I drive programmers crazy. I'm very literal. It said there's brackets in there. Do I put the brackets in there or not? You put the parentheses in, but you don't put the brackets in. Now, why would anyone write anything like that? Wouldn't it be better to write this without the brackets?
That if anything, there needs to be some consistency for it, because sometimes they use the carrots, and sometimes, or not the carrots, sometimes they use the, are those carrots?
But I've seen it put in quotes.
Yeah, quotes, carrots, brackets. I feel like there just needs to be some consistency.
Mm-hmm.
The problem is there's multiple languages recognized, and it doesn't really matter which one you use by Altera.
Yeah.
And it ends up being a problem.
Somebody's trying to teach me how to program. They have not realized how special I am yet. Once I get started, I'll be okay, but I have to have all these questions answered. Don't
worry, Vitaly's a good TA.
Yeah, okay. So yeah, you got all these different things in there. Get it set up the way you want it to. Today's chips, they'll have different control registers, so it's not worth it dwelling on these things. Oh, good. Back to something transistory and physicsy that I like. Okay, this is how the 1T, 1C DRAM cell works. And this is what they're using now. This is modern and valid. Basically, I want to store the charge on C1. And my brilliant epiphany that got me to the point where I could do the DRAM puff was the bottom plate of the capacitor is not at ground. You need to know this for your project because you need to draw the schematic for your project. Amazingly hard to do. This is at VCC/2. This is where people put slashes in their signal names. They put VCC/2. Don't do that. A better name would be VCC2. That's the one that that's the one I use. Okay. It is half of VCC.
You could do like VCC_2, I guess.
You could do that too. That would be valid. VCC/2 is not. Okay. So I've got this capacitor here, and I want to do one or two things to it. The first thing I want to do is if I want to write to, okay, I'm going to select the word line. So let's draw our little timing diagram. So actually, no, the first thing I want to do, let's look at writing first. So to write it, I'm going to take word line high. This is word line. And remember, word line goes up to VCCP because we're going to lose a threshold drop across that gate to source on the transistor. So it's a higher voltage than VCC. after the word line goes hot, well, or before, I'm going to put data on the digit line. So I'm going to put the digit line will either be high or low. I don't know what it is, depending upon whether I'm writing a 1 or a 0. I pull the digit line high. With the digit line, with the word line high, this transistor's on. Whatever's on the drain of the transistor is going to get instantly moved onto the source. So what I'm going to have here, it's either going to be roughly VCC minus the drop from the RDS of the transistor, or it will be 0. So there's always charge stored on this capacitor. Turns out the reason why this is at VCC over 2 is because you have to put less charge to charge it up to VCC minus VCC over 2 than you would have to dump on there to go from VCC to 0. And from 0 to VCC over 2, it's the same amount of charge, just in the negative direction.
Quick question.
Yeah.
Going into the VCC over 2, is that like a input or output line from somewhere else? Like, is there anything coming in, or is it only going out of VCC over 0?
It's a power supply.
Okay, that's the power supply.
Yeah, inside the chip, they generate a lot of regulated power supplies other than VCC, because I'm going to need a charge pump to get me VCCP with a regulator on it. And I'm going to have another regulated supply for VCC over 2, because there's going to be more places where we use that. And I'll show you one of them in about a second. So that's how we write. Now let's change this to read. I'm going to take these scribbles off, and I'll even change colors. Let's go to red. Okay, so we're going to read. So same operation on the word line or the row. I'm going to turn the word line on. Now, before I turn the word line on, I'm going to take this digit line and I'm going to pre-charge it to VCC over 2. This is VCC, and this is ground. Okay, so I pre-charge it right in the middle. And as soon as I turn the word line on, what's going to happen here, this is going to be either at 0 volts or 1 volt. So it's going to want to either pull up the digit line or pull down the digit line. One way or the other. If there's a 1 stored there, it will pull it up. If there's a 0 stored there, it's going to pull it down. And that's how we read the memory back. We'll talk about the details more in a second. This is going to lead to my first version of what becomes the really horrible timing diagram. It's not so bad now. Now, in our open digit line architecture, remember when we address this thing, the first thing we do is we open a row. So only the cells in this row, and that is a row. I'll even write it down to prove to you that it's a row, even though it's going in the wrong direction. Only the cells in this row will have their transistors turned on. So every other transistor will be off. So when I address this row, only this cell will take data in from the digit line or have data written out from the digit line, because this transistor's off. The D3, this is the column. So this is where data gets read and written. So if I'm reading, it's pre-charged to VCC over 2. If I'm writing, it's either a 1 or a 0. Okay. one transistor, 4 terminals. That's another reason why this is VCC over 2. I'll talk about that one later too. The actual individual cell layout, I need a transistor. Here I've got poly over active. This is the poly. This is the active. This little red square right there is the actual transistor. So one side's the drain and one side's the source. So here's my transistor. It's an NMOS. This side we're going to call the drain. This is tied because it's tied to the higher voltage. This one goes to a contact to the digit line. What this is, what I'm seeing in this picture, I've got the digit line. The digit line is active area. So this is going to be, it's an NMOS transistor. This is going to be N plus. I put a via, so I have an N plus layer here, and we're looking at the cross section now. I put a via in between there, which is just a plug that connects the active region, and the stripe thing above it is a layer of metal. So I have a via which connects those 2 layers. It's a short between those 2 layers between my active and my metal layer. This metal line is my digit line. Okay. There's the gate of the transistor right there, the little red box. The gate of the transistor is tied all the way down the line to the word line. That's the poly part. They just run it in poly so it can be both transistor and it can be connection between all the other ones. So there's my word line. The source of the transistor is this N plus diffusion over here. What we're seeing is we have the active area. We've got a via in, no we don't have a via there. We have an active area. The circular thing is the capacitor. And the capacitor, if I looked at this crosswise, cross-sectionally wise, you have N plus, you have N plus, you have the gate. This is the drain, goes up to metal 1. The drain goes to metal 1. This source gets tied into a buried capacitor that's buried in the substrate. It doesn't go all the way down to the bottom. Let's just say it goes like this. We'll have pictures of this later. So this is a buried capacitor, which is that circular thing right there. And the other plate of the cap has to be tied to VCC over 2. Yeah, okay. And so that is what we're seeing. That is 1 bit of memory. Okay. And that's what the whole thing looks like. Now, when I put I can stack these, I can pack these bits of memory in closer together by sharing the digit line contact. And I already explained to you why we can do that, because only one of these is going to be accessed at the same time. Only one word line on at a time. Okay. So only one word line will have access to its capacitor, and only one capacitor can drive this digit line at a time. So we can get away with sharing the digit line contact. It is 1/2 of a feature that I can squeeze out of here. And it's a big deal how small you can make these memory arrays, because the size of the memory array is going to influence the cost. Okay, so here is the first generation layout of a 1T1C. This is called open digit line. So this is 2 bits right here. Each pair of bits shares a digit line, and I can scrunch things a lot closer together than if I had to do this on every single one. That's the idea behind it. It is one of the most compact ways of laying out these memory cells that they have. It has some disadvantages. We'll get to those. Okay, so I've got the data coming out. There's the word lines going through to the gates. Here's the digit line coming out. And as the digit line comes out, it goes across a whole bunch of word lines, and it's going to go into this thing called a sense amp. Now, a sense amp is basically a comparator. So it needs to compare the voltage on D1 to something else. The trick that they do here is what they do is they pre-charge all, when you're reading, you have to pre-charge when you're reading. You have to pre-charge every single, the digit lines to pre-charge digit lines to VCC over 2. So that means this one would be initially sitting at VCC over 2, and this one over here is initially sitting at VCC over 2. What I'm going to do is that when this digit line gets addressed, the little bit of charge off of this capacitor is going to come back onto this line, and it's either going to raise D1 up a slight amount, or it's going to lower D1 up by a slight amount. So if I compare that to VCC over 2, I should get a good idea of whether it's a 0 or a 1. And that's what the sense amp does. It looks like the magic triangle. It looks like an op amp. They are actually, I believe they're actually using op amps now. The sense amp we're going to look at is kind of a prehistoric one, but it's the same idea. And Brian Calloway is just thrilled that you guys know what a sense amp is when you graduate and how it's used correctly in the sentence. He doesn't care that it's the old latch. It's the same idea whether you use an op amp or a latch. The op amps just get more sensitivity. We will look at the version with the latch. So that's all I want to do is I want to see if this is slightly above VCC over 2 or slightly below VCC over 2. And I'm just comparing it to another pre-charge line in another part of the array. This is another drawback of the open architecture, and there will be more details later. So here are the waveforms. This is the start of what I call the really horrible waveform, and you'll understand when we get there. What I want to do, I start out here, I pre-charge, this is when I'm reading it, I pre-charge the digit line to VCC over 2. I turn the word line on, and this goes up to VCCP, higher than VCC. And if I'm reading a logic 1, what happens is the charge on the capacitor charges up the line and raises D1. Now, if I'm reading a 0, again, I pre-charge my digit line to VCC over 2. I turn the word line on, and then what happens is because I've got negative charge stored here, because this is 0 to VCC over 2, I'm going to slightly discharge that D0 line. And we'll figure out by how much by the end of the day, I hope. Now, when I first saw this, I thought there wasn't something quite right with this. If you notice, it charges a little bit after the word line it starts charging a little bit after the word line goes on. This one starts charging before the word line goes on. That is not a typo. That really happens. It takes a lower voltage to turn this on when it's discharging than it does when it's charging. That is real, and Corey Klein proved that to me.
That's really bizarre.
I might be able to give you the argument later, but it's if I can remember it. So this is the basic thing. Now I'm going to put voltages in here. VCC over 2. VCCP is what the word line goes up to. This is VCC. Notice that D1, the date on the line, does not go up all the way to VCC. It only goes up a small amount. And it also only goes down a small amount. So I need an amplifier to take that small amount, basically a comparator, and turn it into, this one's greater, so I'm going to rail it at VCC, or I'm going to rail it at 0. Yeah. Homework 1 is due Thursday. Project 1's due in about 2 weeks. You have to create schematics in Pixis. I hope you at least attempt to start it and open Pixis up this week. If you have IT problems, it may take a day or 2 to get them fixed. Go through me first. I know how to do this. I have to go through Pete, but I know how to do this without irritating Pete too much. Don't go to Pete yourself. Don't go to ITS yourself, because what happens if you go to ITS yourself is it will take a week to get to Pete. And then Pete will be irritated because you won't tell him what he needs to know. Go through me. I will get the magic words and send the email directly to Pete. He knows me, and he knows I do ask questions like, do you need to put the brackets in? So he can put up with me. So here's the big idea. I've got this tiny little capacitance. My N bit has a very small C. The digit line is connected to maybe 512 different cells. This is a big C. And a small C is like a small tank of charge. I can charge it up to a high voltage, but it's not gonna, if I charge in Q equals CV, I can take this small capacitance, I could charge it up to a high voltage and not have very much charge. If I have a bigger capacitance and I charge it up to the same voltage, I'm gonna have more charge. When I turn on the tap, when I turn on the switch between these two, this small C only has a little bit of charge, so this is only gonna go up a tiny little bit. And this is called charge sharing. In order to compensate for that, we can either make C bigger, which is hard to do, or we can make this one smaller, which is also hard to do, or we can have a very sensitive amplifier that can detect small changes in voltage on the output. That's the job of the sense amp. If you learn nothing else today, it's that.
Confiscate capacitors.
Confiscating capacitors. Okay, so here we go. We got my MOSFET here, and the MOSFET is basically acting like a switch. I've got the digit line capacitance, and I've got the M-bit capacitor. Now, one of the rules of physics is charge is conserved. So the initial charge in the system has to equal the final charge in the system. So I could say, okay, so the initial charge, and remember Q equals CV. This is like the V equals IR of capacitors. So the initial charge on the M-bit, on the digit line capacitance, let's do this one first. It's going from VCC over 2, and the other side's grounded. So Q equals CV. It would be C digit. Just the eraser. The initial capacitance would be C digit times its voltage, which is VCC over 2. And the rest of the charge in the system is added. So the voltage across this capacitor is V cell, which can either be 0 volts or VCC. We don't know what it is. V cell minus the charge, the voltage on the other side. So minus VCC over 2 times its capacitance, which is C mbit. Okay, that's the initial charge. When I close that switch, the charge is going to be whatever the final, I'll have whatever the final voltage is across the capacitor. I don't know what that is. V final times C digit. I did that again. That's a digit, DIG. Okay, just pretend. Times C digit plus V final minus VCC over 2. There's a much nicer version of this on the next slide, times C mbit. So then I can do algebra and I can find out how much charge is shared. That's all I'm doing here. What I explained before, and do a little bit of algebra, find the signal voltage, which is the final voltage high minus the final voltage low. The signal voltage equals V cell, let's write this in a more sensible way, V cell times C mbit over C mbit plus C digit. Digit, that's a D. Okay. So whatever voltage is on the cell is going to, Cm is small. This is big. So what you're going to end up with is this is the sig voltage, V sig. The sig voltage is much smaller than V cell. That's a problem. That's why we need the sense amp. Let's put some numbers in here. So the signal voltage represents how much above VCC, or your pre-charged digit line voltage of VCC over 2, the signal is going to go up or go down. If my cell voltage is 1.65 volts, my mbit capacitance is 50 femtofarads. The digit line capacitance is 300 femtofarads. I'm only getting a signal voltage of a couple hundred millivolts. And you'll see that when you build the project. You'll actually get to measure, you'll actually get to look at things like this. Build it and look at it. It's fun. So that is why I need a sense amp. Now, what this sense amp is going to do, let's look at this. It's a latch.
I had to let you know you got 10 minutes left, Julie.
Okay, good. And I've only got like 5 slides left. Good luck, right? What this looks like, and you can prove this to yourself, it's the cross-coupled latchy thingy. Every time I see those cross couples in here, I'm just going to call it a latchy thingy. This is what it looks like. And these inverters are powered off of ACT is the positive supply, and inlet star is the negative supply for that inverter, for that pair of inverters. Remember from 110, this has 2 stable states. If I put a disturbance on here, where D1 is slightly higher than D1 star, it's going to go into the state where my output is high. D1 will be latched high. If I put a disturbance on here, just like in 110, where D1 star is the highest one, then it will go low. It would go low. The output would be driven low. And it's not going to do anything unless it's powered up. So I need to have ACT high because that's the positive power supply, and I need to have inlet star low because that's the negative power supply. So let's make our horrible timing diagram slightly more complicated. First thing I do is pre-charge the digit line to VCC over 2. Then step 1, I turn the word line on. As soon as I turn the word line on, in this case, I'm reading a 1. My digit line, my capacitor dumps its charge onto the digit line and raises the voltage up ever so slightly. We give it time for it to settle. Then we turn on the power supply on the sense amp, ACT and inlet. ACT goes high, inlet goes low. We have to turn inlet low first because it's weird. That's the ground, and it doesn't work right unless the ground is in the right state first. So we start to pull inlet low, then we start to pull ACT high. As the power supply for this thing turns on, my D1 gets charged up fully to VCC. Now I've got a strong digital signal that I can actually pass to the rest of the parts of the chip.
Yeah, isn't like, what is it? I believe in this same diagram that was in the reading last night, that like right, like this part.
Yeah.
Over here, that's when it's like reading, and then it starts writing over.
No,
here, right? Or
you're not to the reading and writing yet. This is just reading. We have not done any writing yet. All I've done is I've read the cell, I put the charge on the word line, and I've turned the sense amp on and let it go all the way out. We have not gotten to the right cycle yet. That will happen shortly.
Why does the what's it called? Oh, never mind. I see it now. So the D1 relies on the ACT, and it triggers before the NLAT not to be the D1 not.
Well,
right?
no, it's a weird thing with latches. Is like if I actually put these, if I flip these at the same time, it's not going to power up right. When I power up a digital system, I want to have the ground to that system in a stable state before I put the hot side to it. That's about the best way I can explain that in 20 seconds. So these are the power supply. Inlet, star, and ACT are the power supply for the latch. That's all they're doing. They're like VCC and ground for this, but I have to give them different names. As soon as ACT goes high, that latch is powered up, and when that latch is powered up, it's going to pull D1 high, and it's going to pull the other side low to get into one of the two stable states of that back-to-back inverter thing. It's in the linear region here, and it's going to latch either high or low.
Okay.
Okay, so this is with the I/O drivers. This is my data coming off the chip. I'm putting it through drivers, so and I'm enabling them. Once they go through drivers, I have to give them different names. So D becomes I/O, and D star becomes I/O star. And then I've got this other thing here, which is column select, which if the column is true, then I just pass it through those I/O transistors become transparent, and I feed it directly into the latch. A little bit more complicated, and you will build the circuit up piece by piece. We're starting with the 1T, 1C, so it's not horrible yet. And this part. The part you built for project 1 is this, and an array of 4 1T, 1Cs. And you put them all together on a top level schematic, and that's about it. We simulate it for project 2. Okay, now we're getting to the part you were thinking about, Ben. So now when I actually read the DRAM cell, I have dumped all the charge off of that poor itty bitty capacitor. So immediately I have to write that value back or the data will be lost. So we've already discussed the access. We've already discussed the sense. The next thing I have to do is I have to take the value, in this case VCC, and give it time to write it back to the cell. So I leave the word line on and I write, let the cell, let the 1T, 1C. So now looks like this. This is the digit line. This is the word line. I've taken this from, this was VCC over 2. It goes a little bit up, and then it goes up even higher. This digit line's still on. This goes all the way up to VCC. Now I've written a 1 back onto that capacitor. That's the right, and then eventually I can just let it go on. We'll go through this again in like more detail as we just keep getting more and more detail. This is a problem. I don't have enough time to talk about this. We'll talk about this again. But yeah, we'll talk about this again. We're done. Any questions? Yes, Ben. Oh, I just got an arrow from you. That was all. Okay. Oh, let me do roll.
I needed to figure. Zoom wasn't letting me unmute myself. It was only letting me make arrows.
Okay. You've been put in Zoom jail.
Just
like a lot of my Republican friends are now in Facebook jail. It's okay. They're like family. I have to put up with them.
So, just a quick question about so when the cap discharges, that's when it opens, right?
When the word line turns on, that switch becomes transparent in the 1T, 1C, which means the capacitor is going to discharge its capacitance to raise the digit line voltage up ever so slightly. And then when the sense amp turns on, it's going to raise the voltage on the word line, on the digit line fully up to VCC or fully down to ground. Which can, if the word line's still on at that point, that can be used now to charge the capacitor that had been discharged by the operation. Okay, good.
Will we get like lab time to work on the projects, or is it just all on our own time for this?
It's all your own time.
Okay.
You can contact me by email anytime you want to. If it's during business hours, I will generally answer fairly quickly. I can actually go into the mentor system and look at your project and see what's going on. So I don't have to rely on you telling me all the details. If you tell me what you think is going on, then I will look at your project and I can usually, within about 2 or 3 minutes, figure out what's actually going on.
Perfect, thank you.
And with this class being small enough and me having a reasonable class load this semester, I'd say I'm going to be fairly patient with your questions.
Speaking of questions, I've got one.
Okay. Go ahead.
My question is this all just for reading 1 byte at a time, 1 bit at a time, sorry?
Yeah, you can read 1 bit at a time. You can read, if you have a 16 parallel outputs, you could read 2 bytes at a time. If you want to, the next trick would be you leave the word line on and you change the column address. So all the time it takes to charge up that to charge up that word line, and then you could move on to the next set of columns and do that again.
Okay.
It's kind of the details of reading out 1 byte of data at a time, basically, or in this case, a word.
But if you're pulling more than 1 bit at a time, right, then it's going to raise it slightly higher than it was doing before, which indicates that there's more positives.
On the word line, there's only 1 word line selected. And because there's only one word line selected, every other transistor on the digit line on that column bus is going to be turned off. Only one transistor on the column line will be turned on at a time.
Is that different than the things that we were doing before where we have like 64 megabits of memory and it's stacked as like 16, but you're pulling out a word every time?
No, okay, so in that case, I address one word line and I turn on 16 column lines. But on the end of, wait. Okay, so the word line goes across this way. And then I have 16 different digit lines. We'll just draw 4. Digit line 1, etc. And so what happens is only this group is turned on, but this group is being read out by different digit lines. So 4 different sense amps would be triggering at the same time, or 16 different sense amps would be triggering at the same time.
Oh,
But they would be in parallel and they wouldn't be connected to each other. Everything else on this on this digit line is off because they're connected to different word lines. That's the advantage of having a 2D array.
Okay.
Yeah.
And then I guess that means that there's 1 sense amp per digit line, huh?
Yes, or per pair of digit lines.
Prepare.
Yes.
Okay.
I'll explain that later. All of the devil's in the details.
I think my upstairs neighbors are trying to communicate with me through the ceiling.
Using Morse code?
Maybe.
Hey, Julie, I have a question about the homework.
Okay.
So the first question, I'm not sure what it's asking for because it asked for a schematic, but then it said label the same voltages on the 2 first waveforms of figure 1.25. So do you want both?
Hold on.
So,
I've got the notebook in front of me. Homework. Sometimes it's easier to do it this way. Homework. No, that's.
you want 4 drawings is the question.
That is pre-lectures. That is projects. Oh, this is the one that has the tabby missing. I think. Yeah. Oh, and there it is. There's the missing tabby thingy. Homework. I'm gonna have to replace the little tabby thingy. It's that one. That's evil. Homework 1. Which question?
The first one.
Okay.
Are you
Okay.
asking for 4 drawings total? Is that what that is?
Right. So you want to draw 4 drawings before and after the access transistor turns on. So it'll be 4 1T, 1Cs. They're not very complicated. When you at first the word line's going to be off, so it'll be low. The capacitor will either be charged or discharged, so that's 2 of the drawings. So the capacitor will either be at 0 volts or VCC, and the digit line is at the digit line voltage.
Yeah.
Right. Okay. Is that we'll just say VCC over 2. Then when the word line goes high, you draw another schematic and with the word line high, and what's going to happen is the digit line voltage will go up to V final, and the capacitor voltage will also be at V final.
Okay, so what I was asking is, this is like that second sentence. It says, also label the same voltages in the first 2 waveforms for figure 1.25. Figure
Right.
1.25, it's like, it's something else. It's not the schematic. So I was wondering, do you want us to draw that as well?
It's the waveforms. So figure 1.25 is just the waveforms that are going on. Basically the word line's turning on and your digit line's pre-charged to VCC over 2. And you're drawing the state of the 1T, 1C before word line comes on and after word line comes on.
Okay, so you don't actually want a separate
Right.
waveform. Okay.
No.
That's good.
Okay.
Thank you.
Okay, no problem.
if you want to work on homework together, I think I'm going to go into IEEE tomorrow.
I'm not a Flagstaff until Sunday.
Ah, fair enough.
Okay.
Yeah. But I'll see you after.
I gotta go. I've got 380.
Have fun.
Oh, I will.
All right. See you, Julie. Have a
I'll
good
see
day.
ya.
Bye,
Okay,
everyone.
Thanks, Julie.
Bye. Stop share and done.